Thanks, Dave. G'day, my name is Brendan, and I'd like to thank the YOW organizers, especially Dave and Ino, for inviting me back. I'd like to thank you for attending, both present and online, and I'd like to acknowledge the traditional owners of the land and pay my respects to the elders past and present. In the past 5 weeks, I've learned about 5 new startups that are doing eBPF or flame graphs or both. This industry seems to be exploding. It's really exciting. It's also very difficult to explain. Imagine it's 1996 and you're trying to explain to people what JavaScript means and what JavaScript will do to the industry. You'll be playing games in your browser. You'll be doing banking in Netscape Navigate. And Mozilla, it's the old browsers that we used to use. So BPF is similar in that we can now define programs that the kernel runs in a way that you can define JavaScript programs that the browser runs. But it is quite abstract. And so as a way to explain BPF, I'm going to use a concrete example, which is flame graphs, and how eBPF is helping with flame graphs. Hands up if you're already using flame graphs, if you know that you are. OK, so we only have a dozen people. So hopefully, a couple of weeks after this conference, that will be most of you. If you're looking after software, you'll have created a flame graph for your product. So I'll cover CPU flame graphs, eBPF, and then how they fit together. CPU flame graphs show a CPU profile so you can understand what is running on CPU. I've begun by showing a stack trace, so running JStack on a Java program. You should be familiar with stack traces, especially when your program blows up. This shows main called function A, called function B, called function C. To understand what software is doing, you can collect lots of stack traces. That's a CPU profile. There's different ways to do it. You can do time sampling, where I'm taking a stack trace every 10 milliseconds or 100 milliseconds. Or I can instrument function calls or method calls, and then gather information on everything, every method call. That is often prohibitively expensive in production, especially for back-end servers, which I spend most of my time on, where you may have 200 CPUs all running Java threads, doing millions of methods per second. A more practical way to do CPU profiling is to do time sampling, where every 100 milliseconds or so, I take a stack sample across all of those CPUs. Now, if you look at those stack samples, I've got function A was running, and then A called B, so the stack is now B and then A. And then we went off CPU. We didn't sample while we're off CPU. You can sample when you're off CPU. It's called real-time profiling, but there's other ways to get that done, which I'll get to. If I were to draw those stack samples together, then it would look like this. So I've got each tower of rectangles is a stack, and the x-axis is the passage of time. I've just picked random warm colors to help visually differentiate all of these boxes. Otherwise, it'd be a big screen of boxes of the same color. I can do this as a visualization, but when you're looking at a server with 60 CPUs or 200 CPUs, I might be profiling it. I like to use 49 hertz, so I'm profiling it 49 times per second. Not 50 hertz or 100, because I don't want lockstep sampling with some programmatic activity where you're waking up every 100 milliseconds, and then that will skew the sample. And so we like to put a bit of jitter into our sampling, or just pick some weird number like 49 or 51. So let's say 49 samples, and I've got 60 CPUs. You end up with lots and lots of these. So if I was to visualize this, they would all end up being so narrow you couldn't draw the function name on the visualization. But there's a way to help fix that. And that's where I can merge together adjacent frames. So I've got frames, so I've got D, D, D in a row. Why don't I just merge them together? That can happen for a long span of time, and so the visualization now becomes a bit more practical because I have room in a profile to label things. Now I'll show you a real one. So this is a vertex application, and I'm showing the passage of time on the x-axis And these are all stack samples. And if the adjacent frames have the same name, then I can join them together, and I've got more room to put the label. So you can see about halfway down this thing, which I haven't named yet, you can start to see the names. Well, that's an improvement. Otherwise, it would just all be hair. But there's a way to go further. If instead of having time on the x-axis, I do the alphabet on the x-axis, then I can merge things much better. So I now get longer spans can be merged. The previous visualization, which was still mostly hair, now looks like this. Wow, I can now read it. I can now understand that complicated profile all at once. It's a bit strange because the x-axis is not the passage of time. But the width is proportional to presence in the samples. So I can see 80% of the time I'm in this stack, I'm in IO neti, channel in IO, and so on. I can read it. I can print this out, and it works on paper as well. I don't need a computer to be able to zoom in and zoom out, which turns out to be a useful property when you want to include these in books and articles and JIRA tickets as images, screenshots. People can tweet them. People have, on Twitter, this is their flame graph for their software, and it just makes sense as a picture. You can browse it and do performance analysis just from one PNG or JPEG. I see these showing up on GitHub all the time when people are working on issues. Here's my performance patch. Here's the flame graph to help improve performance. I'll talk about the origin of flame graphs. It's interesting nowadays. There's so many talks on flame graphs and eBPF. Other people are talking about flame graphs and explaining how they work. I can talk about why I invented them. It was 2011, and I was doing performance analysis of MySQL for a production issue between two different operating systems. And on one operating system, I had the dtrace profiler and did CPU profiling. It printed out frequency counts of stacks. And so I've truncated the output. The last two stacks there, I can see we're doing do command, dispatch command, calculate sum of all status, add to status. So I looked at this and I thought, okay, so maybe there's why is the performance different? Why is the performance different between these two operating systems? Maybe it's related to that one. We're doing status, and it's more expensive than the other one, just based on the last stack. But that's just looking at the last two stacks. That's not looking at the full output. So I spent a couple of days digging into this theory, that it was something to do with sum of all status, and that would reveal the difference, and it was a dead end. It was somewhere else in the profile. It wasn't the most frequent stacks. The full profile looked like this. And the two stacks I just had on the previous screen are right at the end. And I realized this could take months. It could take months for me to understand the profile. And we needed to understand the profile immediately. This was an important customer. I thought maybe this is a problem that a visualization can solve. At work, it was not a great environment to be mucking around with visualizations when we had this urgent customer issue. And previously, people I'd worked with had been criticized for wasting time on visualizations. So I didn't even feel like I could do this on work hours. So I did this out of hours. I went and tried some profiling visualizations to make better sense of this output. And there was a couple from my former colleagues at Sun Microsystems, one by Real Neil and another by Roch Bobonnet, where they were doing that time series stack trace that I initially showed, and I called it a hair graph. And so I tried that, and that was actually based on function tracing. Since I was doing profiling, I knew I didn't know the passage of time. It was a coarse measurement. And so I switched the x-axis to be alphabet, and the same profile looked like this. And wow, I can actually understand it. Rock and RealNil, their visualizations, which RealNil's made his online as open source, they used a completely random color palette to differentiate between adjacent frames. And it kind of looked like an angry fruit salad. I restricted it just to be the warm colors, just because I thought it visually looked nicer. And it immediately became known as flame graphs. Looking at this flame graph, the stacks that I was investigating earlier are here on the left, and you can see that's only 5% of the profile. This is why it ended up being a dead end. Most of the time is over here in join exec and create sort index and file sort. And so that, I can immediately just look at it and say, oh, it's 80% of the time is over here, and then 30% is over here, just by comparing line lengths, by comparing bits. So it was awesome. It solved the issue. Just to show how it looks like using a different profiler, this is Linux Perf. Linux Perf does this hierarchy view, so it actually tries to coalesce the output better. It's still too much output to read through, and so that's the full perf output. And for that example, there's the equivalent flame graph. It fits on one slide. I can print this out. I can put it in a book. You can still read it. So that was great. One of my colleagues at the time, he was leading Node.js at the time, and he looked at it and said, oh, this is too weird. No one's going to use it by doing the alphabet on the x-axis. And then 2 days later, he'd been playing with it, and he said, I don't know how we ever did Node.js performance before this existed. And so it quickly got adopted because it was badly needed. So that was at the end of 2011. In 2013, a Google engineer, Ilya Tikhonovsky, filed a bug on WebKit to say, this visualization can give developers a clue what's going on with performance without expanding the entire tree. Links to my blog post. Does the prototype, and then years later it now looks like this. Anyone use this visualization in Chrome DevTools front end? Lots of people. Okay, so that's become much more used. It depends on with your back end or front end. But this is different. So this is the passage of time. And so it ends up being a bit of a hair graph. Now, I should just email Ilya to ask. It may have been deliberate. And notice Ilya called it flame chart, not flame graph. And so now, whether that's an accident or deliberate, I use that as terminology. Flame chart is time on the x-axis. Flame graph is alphabet or something else on the x-axis to show the full population. The hair graph from flame charts is not that bad because JavaScript, V8 is typically single-threaded, and you don't have all of these samples from different CPUs at the same time. And so it kind of works. So you do get these series that can join together. So it's not as bad as my hair graphs earlier. So I feel it may have been deliberate. They've changed it. They've gone back to time. And they have called it flame charts. I have posted bugs a long time ago for both Chrome and Firefox and said, that's great, but we want both. I want a tab so I can change between flame charts and flame graphs. So you can basically take your data set and then turn it around and use different visualizations to understand it. And Firefox Profiler has done that. I just loaded the same profile into Firefox Profiler, and now I can see it's not so much of a hair graph now. That's the flame graph tab that shows the whole population. So you can, if you see it, it's like, well, I'm spending 20% of my time in C. Yes, I'm looking at the YOW Perth website in the Firefox Profiler, just as an example. But it's not that interesting. And it looks like it's obfuscated, so I've only got, it's been passed through one of those obfuscators. I've only got, or minimizers, so I've only got a couple of character names for the functions. But you get the idea. So I get to see the big picture more easily, and I can switch between them. So flame graphs, x-axis of the population, alphabet sort could be another type of sort, like based on call site. flame charts, x-axis is time. Just quickly, to go through flame graph interpretation, the top edge shows who is running on CPU and how much. So you can immediately compare the widths. And I look for plateaus because that's where the CPUs are spending most of their time, and that's where I can find optimizations. Top down shows the ancestry. So G was called by F, was called by D, and so on. To understand a flame graph, you can compare the widths. So how much time is spent in B and its children versus H and its children? Looks like it's about 3 times more in B than H, like 75%, 25%, just visually. So you can make a lot of sense of flame graph. You can mouse over, in the real visualization, you can mouse over and it'll give you the percentages. And it's about time I showed that. So here's one of the flame graphs. If I mouse over, it'll give me a pop-up, 74% there. But I don't even need to mouse over because I can see the bulk of the profile just by comparing it visually, which is also helpful if you print it out. It's on paper. In the interactive visualization, you can also click to zoom. So I can zoom into all the details. And importantly, I can search. So I typed in the word command. And then in the bottom right, it says matched 78%. I use that number all the time because as a performance engineer, my job is a lot about prioritizing. It's not about finding a performance issue. There's lots of performance issues. You can go to an open source repo for some software, type performance into the tickets, and have like multiple pages of performance bugs that have been known for years. It's about prioritizing the performance issues. Which ones matter for the company? Which one should we fix first and then second? And so being able to quantify the time is super important. Right. Okay, so 7.8% in the right path. So use that feature all the time. And then the last part for interpretation is colors. What do the colors mean? They're randomized to differentiate frames. That's what happens when you don't randomize them to differentiate frames. Well, it's okay, but the towers can kind of blend into each other visually. So maybe I should file a ticket and say, just make the colors random. So often randomized or varied to differentiate frames. And I'll often use the color hue to show the code type. So green for jittered code like Java, red for user level, orange for kernel, and so on. Just come up with whatever color scheme suits you, that's fine. At Netflix, some developers would permanently highlight their own code in magenta or something, so every time they got a flame graph, their bits of the flame graph were always highlighted so they could always find it. And I also use color for other dimensions. So if I want to show cycles per instruction or other metrics in the flame graph as well, I can use a color scheme. That's flame graphs summarized on one slide. So visualized as a collection of stack traces, x-axis is population. My original version was written in Perl, and I did it like in 2 hours, one night. I love Perl. Turns out most people don't love Perl. So I was giving an in-person presentation at a major company early on, and they said, oh, we love flame graphs, but can you please write it in Python? No, you're just going to have to use Perl. Now, actually, I ended up writing in Python, but unfortunately, there was an internal project that didn't get published. I don't mind people rewriting this and other stuff. If you prefer other stuff, that's totally fine. In fact, I've been spending a lot of time with a D3 version, which was created by my colleague at Netflix, Martin Spear. I was talking to Martin about, we want to do more things with flame graphs beyond what my Perl version could do. And so Martin said, yeah, let's do it in D3. So he's created D3 flame graph, and we use that in Netflix's internal continuous profiler, Flame Commander. Unfortunately, both Martin and I left Netflix before we open sourced it, so I don't know if my colleagues who are still there will ever open source it. It was a cool tool. But at least we did open source the D3 profiler part. And so that's now being used by companies to do flame graphs. In fact, I've had demonstrations from people showing me the D3 flame graph where they say, Brendan, check this out. Don't you love this, how it does animations? You can zoom in and zoom out. So I think I've got one of his flame graphs open. Oh, look at that. It moves. So D3 does animations. Yes. Whip. Yeah. Yeah. Whip. And it's like, yes, I know this because I was with Martin when we created this. People think I only ever did the Perl version. Maybe because I love Perl, but no, I did help with this as well. So it's great. But the point was to do more than just the zoom animations. We wanted to be able to do change the merge order, click on a frame and say merge around this frame, and all sorts of other things of D3, which we still need to get done. Linux CPU flame graphs in 3 easy steps, just to put it in the slide. You can use my Perl software, but you don't have to. You can use the D3 version, that's fine. You can write your own version, doesn't matter. There's a version in Rust someone's written. Here I've got perf record and then perf script, and then we output it, and we've got the SVG. It includes embedded JavaScript. Some runtimes, like the JVM, require extra steps so that you get stacks and symbols for this to make sense. So that's CPU flame graphs. So there's Linux 2.6, and later, perf record, it outputs to the file system, to a perf.data file, every sample with timestamps. That takes overhead. It takes CPU cycles, it takes file system overhead. Eventually the block device, the file system and block device layer will flush it to disks. So we've now got disk I/O. Then we reread it again with perf script. And then it does symbol translation for every single stack trace. Hopefully it does some caching. And then we feed it into stack collapse, which then frequency counts stacks. And finally, we feed it into flame graph, which spits out the visualization. I said someone rewrote it in Rust, and their selling feature was they rewrote stack collapse.pl in Rust, and stack collapse perf, and they said it's like 20 times faster in Rust. It's like, yes, that's cool, and I should be more excited about this as a performance engineer, but the new way of doing this is I'm just getting rid of that stuff. Like, we're not going to do that anyway. I'm going to have an eBPF program summarize the stacks in kernel context and do the frequency counts there, and just emit the summarized output to user space just for rendering. This is the first thing of many that eBPF does to help with flame graphs. So what's eBPF? BPF itself is an arcane operating systems technology from 1992 that stands for Berkeley Packet Filter. And if you did TCP dump with a filter expression, that would get compiled into this bytecode, and then the kernel would turn it into the machine code so that it could execute in kernel space close to the device driver and speed up packet filtering. I didn't really know about it, even though I'd worked in performance engineering. I guess I sort of knew that the TCP dump had been optimized, but it was very obscure. One weird detail about it, however, was the reason it exists, by the way, is previously, if you look at performance monitoring, there's been a number of companies that are doing network sniffing, and they're doing application performance monitoring by basically running libpcap on your interfaces and then looking at all the packets. There's big problems with that because at big sites you can be doing millions of packets a second and the overhead is just prohibitive. So I'm not a fan of sniffing all the packets. I want a better way to do this. And BPF was helping with that. So if you say, I don't need all the packets, I just need the sins, TCP sins, then I can come up with a filter expression, and that would reduce the overhead. So user space is only getting things that match that expression. But again, obscure technology. What was interesting about it was a virtual machine. There had been a number of projects to try to get a virtual machine into the Linux kernel for all sorts of cool reasons. Someone was trying to get Lua into the Linux kernel, KTAP was trying to get a virtual machine into the Linux kernel, and they kept getting rejected because it's pretty scary to put a whole virtual machine into the Linux kernel where people can just run stuff. An engineer at a startup called PlumGrid that's doing software-defined networking, Alexei Startoyov, he wanted a way to do software-defined networking in the kernel, but to have a virtual machine so that he could define in user space the rules for software-defined networking. and the kernel would execute it efficiently. And Alexei was very wise and clever about going about doing this. He did not repeat the same problems of the past of, like, here's an entire virtual machine. Linus, can you please accept this massive change? What Alexei did was broke it up into little parts to feed it in bit by bit. And so Alexei realized there's already a virtual machine in the kernel that no one knows about. It's called BPF. That's the thing for packet filters. If I extend that a little bit, and then a little bit more, and then a little bit more, we'll eventually have what he needs for software-defined networking. And he also thought it can go even beyond that. So the year was 2014, and Alexei had these very interesting patch sets floating around on the Linux kernel mailing list. And I got him to visit Netflix, where I had him explain, like where are you taking this and where's it going? And he wanted to go far beyond software-defined networking. He said, this can be used for tracing as well. And it's like, well, this is pretty interesting, but I could see that where other people had failed by doing too much, he was being more practical and pragmatic. So I made a deal with him. I said, if you give me the tracing hooks, because it didn't even hook to tracing events at that point. If you give me the tracing hooks, I will write the software, the user space, the tools to do tracing. And so Alexei did. I was testing his patches before they got merged. They got merged. He kept building it and building it. Daniel Borkman got involved. He was a Red Hat engineer. And so Alexei and Daniel are the co-maintainers. And nowadays, it's grown into this whole ecosystem where there's conferences. It's taken over Linux conferences and KubeCon, and everyone's talking about eBPF. It has grown into a fully fledged virtual machine in the Linux kernel. And you can define software and user space that the kernel then runs. For SDM was the original use case, but DDoS mitigation, intrusion detection, container security, observability, application performance monitoring, and so on. In the past 5 weeks, I mentioned there's 5 new startups. Some of them are doing zero instrumentation application performance monitoring. So they're using these event targets like uprobes to look at your HTTP calls around your stack or your gRPC calls around your stack without you having to modify your code at all. So the moment you do application performance monitoring, I might take OpenTelemetry and then I make changes to my code so it's instrumented. With the new ones, you don't have to change your code at all, which might be beneficial if you don't have access to change your code. So it can go into the user space, address space, and then live change those instructions. In a safe way, we've done this for years. uprobes has existed for a long time. Live change those instructions so we can do some instrumentation. Pretty exciting. In fact, there's one of the developers from one of those startups just met me this morning. He's here in Perth. Firewalls, device drivers, and there's going to be more use cases beyond this that are happening as well. All of these programs, they go into a verifier to make sure the eBPF program is safe, and then it gets turned into, eventually gets turned into machine code that gets executed, and they attach to event targets. So eBPF is an event-based program. I've got a slide to say, I may call it BPF and eBPF interchangeably. So early on, Alexei wanted to call it eBPF for extended BPF. But it's grown into something that's way beyond Berkeley packet filters. And like every presentation we ever give on BPF, we have to explain, oh no, it does more than packet filters. It does all sorts of things. So Alexei said, I know, we'll just say eBPF is no longer an acronym. It's just a name. It's like, that's terrible. Like, why would you do that? Well, Alexei used to work on LLVM compiler, which is also just a name these days. So I guess there's a bit of history there. I guess the real reason is we have not had professional marketing help with eBPF, because I'm sure in the early days, a professional marketing person would say, no, you have to give it a real name. You have to give it a name like Docker or something. You just can't make this stuff up. But we're stuck with it. So it's eBPF. It's not an acronym. It's just a name. In kernel engineering, though, Alexei changed his mind again and said, I know, I just want to call it BPF because it's also an instruction set, and there's a precedent for instruction sets having 3 characters. So x86 and ARM and BPF. So within kernel engineering, if you look at the kernel engineering mailing lists, we just call it BPF, the kernel engineers. But publicly, we try to call it eBPF because it's just fractionally more Googleable than just BPF. It is a huge change, though. So for 50 years, we've had one dominant operating systems model, application system calls, kernel and hardware. That comes from Multics, where it had multiple rings of security. And you can see we don't have multiple rings, we just have applications and kernel. We just use 2 rings, and that's coded into the processors themselves. They understand privilege rings, and if you do instructions in one ring you're not allowed to, you get a fault. Modern Linux has changed that, and it's the first widespread change to that model. So now, apart from user mode applications that syscall into the kernel, we now have kernel mode applications that use BPF helper calls into the kernel. There's been lots of academic papers over the past 30 years about let's do microkernels and hybrid kernels and this and that, but they've not really seen widespread use, like Plan 9 and Inferno. The Microsoft Windows kernel was the closest to do different things because it's hybrid-ish, the way things can be defined differently. But this is the first real change to Unix or Linux. It also changes, it provides an alternate process state model. Here's the process state model we've used forever. So I'm on CPU, user in kernel space, and then I block for some reason. Maybe I'm waiting on a resource, I'm waiting on a lock, I'm just sleeping. BPF program state model is event-based, so you enable a program on an event. When that event fires, you go on CPU. You can do other kernel code through helpers only. It's sandboxed. There are spin locks, and in some cases you can even, this is a new addition, you can sleep in a BPF program. That was added especially for doing user space memory access when it hasn't been faulted in. We needed to be able to sleep to allow the fault to happen. Alexei has been taking it further and further. This is from NetConf 2018. In the early days, from 2014 to then, we had a max instruction size of 4,000 instructions for BPF. So we're all writing these mini BPF programs that do this and that. And then Alexei said he's going to change the maximum instruction size to 1 million. And he said, I want people to be able to write a Rubik's Cube solver in BPF. People can write anything in BPF. And he's always been visionary, and this is the turning point. Was like, this is going to be huge if we grow it and allow major applications to be coded in BPF. He's also shared at Facebook, they have 40 BPF programs running by default on every Facebook server. And I shared when I was still working at Netflix. Netflix has 14 BPF programs running by default on every Netflix cloud instance. You may have BPF running, you just don't know it. So it is starting to get used by lots of things. Another way to understand it, so I've got user mode applications, and that calls into kernel mode applications written in BPF, where they're faster, based on events, either kernel events or user space events. And it's been said multiple times, the modern Linux is becoming microkernel-ish, because we can redefine parts of the Linux kernel. You want to have a different TCP/IP stack. You want to have a different way of doing routing packets, a different CPU scheduler. You can define that in BPF, and we've been adding all the hooks so that that can be plugged into the kernel, which means ultimately you have a smaller kernel and more of it is user space defined. Stephen Restet, one of the kernel maintainers, said BPF will replace Linux, and there was a period of time where all of the Linux maintainer conferences were just overtaken with eBPF. Also, Microsoft are right now adding eBPF to Windows, the Windows kernel. And so I'm on the BPF technical steering committee, and I meet with Microsoft every 2 weeks. So they are busy at work doing this. And if I thought the ecosystem was exploding right now on Linux, imagine what is in store for us next when it's on Windows as well. How does it work internally? You have BPF instructions go through a verifier that makes sure it's safe, it's secure, it doesn't do anything naughty. That then goes to a JIT compiler that turns it into machine code, and it then runs. If you want to do other stuff to the kernel, like redirect a packet, remember it came from software-defined networking, there are BPF helpers to do that. If you want to collect a stack trace, because I'm doing profiling, there's a BPF help. Originally, there wasn't a BPF helper, and I published the first BPF profiler by I manually walked the stack in pure eBPF, which is interesting, because maybe we do want to do some custom stack walkers, that has been done before. But there's a helper for that makes it easier. There's map storage, and when events fire, you get some context with the event. There used to be an interpreter, but we compiled it out of the kernel. Gone. Everything has to be JIT compiled now. And the reason for that was Spectrum Meltdown. With Spectrum Meltdown, everyone was busy. I was busy doing the performance analysis at Netflix. Everyone was busy changing their code and deploying new versions. But the BPF bytecode, all we had to do was update the JIT compiler to do the mitigations. And then all of that bytecode was then safe. And so after that, we realized there's huge benefits for the JIT compiler. We should just make it, everything should have to do the JIT compiler, because it helps us quickly patch over security vulnerabilities. One important part of this diagram is once you're running your machine code and you look like other kernel code. Previously, I used the word virtual machine, and so you might start thinking in your head, oh, it's like an emulation, there's layers and there's overhead. No. But it's like a virtual machine, but by the time you're running, it's literal machine code. It looks like other kernel code. So it's super fast. Is BPF Turing complete? I need to delete this slide because it's no longer becoming funny, because it is getting closer and closer. So BPF programs have to be bounded. They have to complete. You can't have an infinite loop in a BPF program. And so that makes it non-Turing complete. But since I was using that slide, we have added bounded loops and all sorts of stuff. I've tried to give you an idea of why it's different from other software. So user space, kernel space, and BPF. User space, it has, you can compile it in any way. The failure mode for user space is an abort. The failure mode in kernel space is a panic. BPF has a safe failure mode. You just get an error message. So it's a safer environment for doing kernel development, because if you want to write a kernel module or do something else and things go wrong, you panic the kernel, the whole machine stops. Or depends on your sysctl settings. Resource access is better than user space. You don't have to syscall or fault to I/O, but it's not quite as good as the kernel because you have to go through restricted helpers, but it's still pretty good. It is secure. It's verified in JIT compile. That's a big selling feature. And it's because of those two columns, security and failure mode, that previously, if a startup came to Netflix and said, we have this great new product, please run it, it's a kernel module. We'd say, no, like the kernel module could panic our service. Actually, that doesn't matter so much because Netflix uses the chaos engineering and everything's safe fail. The bigger problem is there could be security issues because you're basically running as root. It's like, please run my software as root. Now with BPF, it is verified, so there are security assurances, and it's not going to panic the servers either. So it's much more appetizing for startups to come up with advanced technologies and convince companies to use them if they're eBPF based. Because of all the other features, I was at another Linux maintainers summit last week, Plumbers, and Alexei said that BPF should become the environment of choice for kernel engineering. And that's really putting it out there. That's saying kernel engineers should prefer to write new things in BPF over C. It's pretty dramatic, but he has not been wrong in the past because it has just been this huge change in how we're doing everything. So an example use case, back to some examples so that we can better understand it. BPF observability or tracing. And flame graphs is my main example use case. BPF enables a new class of custom efficient production safe tools. Linux tracing used to be a mess with cute ponies. So when I started Linux in 2014, there's ftrace, perfevent, systemtab, ktab, LTTNG, dtrace for Linux. There was actually 14 different traces for Linux. And none of them were really complete and did everything for every environment, like worked across all the distributions. eBPF has given us the traces we've been after for a long time, and so the main two we're using now is BCC, libbpf, and BPF trace. These cute ponies were actually created by my wife, who is a professional tech marketing person. She works at Intel as well now. And she'd been creating these forever and used as part of merchandise. But she hasn't officially been working on eBPF because I'm sure she would have told us to rename it long ago. I've created eBPF performance tools. These are all open source. You can run them. They're all online. There's also a book, if you want to get a book, where I explain the background and how to interpret them. My diagrams, people love my arrow diagrams. Here I've got all my BPF tools in red with the new ones I did for the book. Again, they're all open source, so you can use these to understand your systems. Just a few concrete examples. Julia Evans said, I really wish I had a command line tool that give me stats on TCP connection lengths on a given port. Absolutely, and so I created TCP Life for that. So you just run it, and it goes and instruments the kernel. It does not instrument per packet. Like I said, I'm not a fan of that. I'm just instrumenting TCP state changes because it's low overhead. And then I can pull out things like the details, the duration, and the kilobytes sent and received. People have turned this into products. And so they just feed this output into GraphViz, and you do your directed acyclic graph. Here, we can map your environment. They used to do that using packet filtering. It was too expensive. But now you can just do it based on my tool. It's basically negligible. Netflix runs a version of this 24/7 and sends all the output to S3 for flow accounting. They did a blog post on it. And there's the local, you can match on ports like Julia asked for in the first place. So my tools in BCC, they've got usage messages, they've got options. Another popular tool, exec-snoop, what processes are launching. Again, it uses, this version's using eBPF to efficiently fetch things. And I can see, it's interesting to run it on environments, and you'll be surprised at what's running. It's like, why are mkdirs running? And like this would run all the time, like constantly in a loop on some of the instances I was working on. And it was just like a haywire shell script that no one knew about. Biolatency, another great example of eBPF. I want to know the latency of disk I/O in more detail than just IOstat, just the system metrics that tells me average latency. And so I want a histogram. I want to be able to see a power of 2 histogram where I can see the distribution. With eBPF, my program measures the start and end of disk I/O, does the latency calculation, and it does the grouping into buckets, all in kernel space. And the only thing I emit to user space is what I've highlighted there, an array of like 8 numbers. So the overhead of this is so small. The previous method would do this is we would dump all the disk I/O events to a giant file, we'd post-process them, it was very expensive. Now just do all that processing in the kernel. And like the rest of this stuff, the ASCII distribution plot, user space just draws it. But you can feed that into UIs as well. So I can do latency heat maps. That's a prior invention of mine. BPF trace read ahead, another nice example of mine. For a long time, I'm like, are file systems, when they do read ahead, are we ever using the pages they read ahead, or is it wasteful? Should we tune it? Is it polluting the cache? And the source code fits on a slide. That's the entire source code for read ahead in BPF trace. You don't need to understand all of it, but I'm just picking on a couple of kernel functions, pulling out the information I need, printing it out, done. So it's great. So you can do this on the fly. I can walk, you can have a performance issue no one's seen before, somewhere in the kernel or in the applications as well, and then without even restarting anything, you can start instrumenting functions. It uses dynamic instrumentation, which has been around for a long time, and that can change instruction text live in a safe way. We'll pause threads and pause processes, do the change, unpause them, so that you can instrument anything. In fact, the kernel version has optimization, so it's not even doing it's hooking into the ftrace framework. But For developers, this is all great, but as soon as I put a slide of source code in, I don't want to give you the wrong idea. Don't know why the background is blue. For developers, I'd like you to think like a sysadmin and not like a programmer. And to start with, just use the tools. Install the tools and use them. Don't worry too much about programming this stuff. I was around for the big change from Telnet and FTP and rlogin and a few others to SSH. That was at the start of my career. I was a sysadmin. And at the time, cryptography was new. And I got into security, and I was doing security consulting, and I got to the point where I could draw diagrams of cryptographic algorithms like DES on a whiteboard, and I was teaching classes on this, and I was teaching everyone, like, here's how you can implement DES, and here's how you can implement this and that, Bluefish, reading Bruce Schneier's applied cryptography. Now, looking back on that, it's, what were we doing? I mean, this is how we were learning cryptography back in those early days, but nowadays, like, why would you do that? You just use a library, use OpenSSL. Like, most people here don't need to write a cryptographic algorithm. You just need to know, it exists, and you need to use the library, the end. And so I'm seeing this same pattern with BPF, where people are like, oh yeah, this is great, I need to learn how to code it. It's like, oh, hold on. You just need to know it exists, and then use it. Like, maybe you can code it if you want to. But at most companies, even big companies, like at Netflix, there should be fewer than 10 people out of 3,000 engineers that would ever write BPF code. But the rest of the engineers need to know it exists. So they know to go and bug that team and say, hey, we've got a new issue. I bet eBPF can solve it. Help us out. So that's being practical. You all need to know it exists, but only a few of you will ever really write the code, and that's fine. Think like a sysadmin, install it. It's all open source. And run the tools. And these are installed by default at Netflix and Meta. So like exec-snoop, anything periodic running, from crontab, open-snoop, any misconfigurations, and so on. And you can print my diagram for your office wall and use it as a checklist. I know I've got a block device issue. Try these tools. Just try them, see what they show up, anything weird. Recommended tracing front ends, BCC and BPF trace are the main ones if you just want to run tools. To hack up new tools, if you want to start doing that, it's BPF trace. If you want to spend weeks building a BPF product, then you'll get into BCC, libbpfc, and other interfaces as well. If that seems super weird, it's like, oh, why are there so many different interfaces? As analogies, in Unix, if you want to run tools, it's in user bin. If you want to hack up new tools, it's in bash and awk. And if you want to spend weeks developing a product, then it's C and C++ and Rust and other languages as well. Oh, phew, back out of the blue slides. Observability of eBPF, just to mention this quickly, well, this is great, but BPF programs aren't in proc. So when you run top on your servers, you won't even see them. So it's a work in progress, but we're inventing a way so that there's a whole different ecosystem to find out what BPF programs are running. So BPF tool will list things. Kprobes are attached to these kernel functions. You can also dump the assembly if you really want to for programs that are on your system. Analdo has been working on CPU profiling of BPF programs so that you can do performance analysis. And at LSFMM, which is one of the kernel main summits, David S. Miller, the networking maintainer, said we should be able to single-step execution. We should be able to take core dump of a BPF program of all state. And there's a new eBPF debugger project to try to do that. I was going through my slides, and it's like, why do all my conference pitches say 2019? It's because I haven't done conferences for the last 2 years because we've had the pandemic. And so I had all these pictures of people giving talks, and it was a reminder. It's been a while. I keynoted the start of that conference on BPF, and Dave gave the closing keynote on BPF. So we had the bookends. Like I said, the BPF has been taking over Linux conferences. Future predictions, more device drivers including USB on eBPF monitoring agents. There's application performance monitoring. There's the zero instrumentation performance monitoring, where it's just tracing your HTTP calls via the library or gRPC calls or whatever, so you don't have to change code. Intrusion detection systems, TCP congestion controls. There's already been work to do that. CPU and container schedules. There was work last week at the Plumbers Conference about that. And we're just finding more and more uses for eBPF. Now, finally, that's all great. Your CLI tools are awesome. But practically, people find more performance wins from flame graphs than my advanced tools. So tying them together, eBPF flame graphs. I've got a tool in BCC profile that does it. That's the command line. Flamegraph.pl does have some options, so you can customize the output. And it gives you lower overhead profile. It makes continuous profiling more practical. It also makes off-CPU analysis practical. So I mentioned at the start about this idea of real-time profiling. With CPU flame graphs, you're only looking at the red circle, the pink circles. You're only looking at what's on CPU. All the performance issues when you block, how do you analyze them? Like, I've written books on this. It's like, well, you use this library of these tools and that tool and this to look at disk I/O and that to do lock analysis. And it's advanced, and it's laborious. There's a lot of stuff. We've always wanted like one tool to look at it all, similar to flame graphs, that does all of those blocking states. And that's off-CPU time flame graphs. And now the x-axis is, instead of samples, we're looking at off-CPU time, but it's still population on the x-axis. And then I can drill into bits and say, oh, I'm blocked on file reads from disk, directory reads from disk, and I can proportionally see the time. Here I'm looking at the tar command. And so I can quickly analyze off-CPU time, just like I can quickly analyze CPU time. This uses eBPF to make it efficient because the off-CPU tracing does have a high overhead because you need to do stuff on every scheduler event, every context switch. And I get a bit nervous about that because that's going to be a million events a second. But kernel tracing is very efficient. Last time I did the benchmarking, the minimum overhead was 69 nanoseconds per event. So yeah, we can extend the scheduler a little bit and do some of this tracing with eBPF because the overhead is small enough. So CPU flame graphs plus off-CPU flame graphs allow us to see everything. They're not widely used yet because there's still a bunch of work to do to get off-CPU flame graphs to work. So yeah, just zooming into gzip latency. One piece of work that needs to be done. The off-CPU stack often doesn't show the root cause of the latency. So in this example, gzip was waiting on pipe read, was waiting on pipe wait, and then waiting on someone else. And so I've been working on off-wake time flame graphs where you put the waker stack on top of the off-CPU stack so you can see who you were blocked on and who they woke up. And again, it needs eBPF to be able to do this in kernel context efficiently and merge these stacks together. And so now this is amazing. This example, I was just doing like tar gzip to do an archive, but you can see how gzip was blocked on a pipe, and that was blocked on tar. So I've got that waker stack. So you can see it all together. This is great. But there's more work to do. So practical off-CPU flame graphs is a work in progress using eBPF. Other types of flame graphs, so you can, if you want to, you can go into disk I/O separately, network separately. Malloc flame graphs, so you can understand memory allocation in applications. Custom stack walking is another thing we need eBPF for. A lot of the flame graphs do have little bits that are broken, and it's especially the case of off-CPU flame graphs because they often go through libc, and libc is not compiled with frame pointers by default. In fact, I was just seeing this earlier. Yeah, this example, down here, there is this write path. I go into libc, and there should be some bash frames underneath this. But these towers on the left should actually be on top of the towers on the right. They're actually disconnected. They're broken because we got into libc, and libc broke stack walking and it disconnected the stack walk. If you work at a major company like Netflix and Facebook, we compile all the software with frame pointers so that stack walking works. But I've been trying to work with Canonical and other distributions, and I've got email I've got to respond to about this so that we can fix it in the other distributions as well. So this isn't just a cool thing that the FANGs use, but everyone gets to use full stack walking because we've done the effort to get this fixed in all the Linux distros. So that's another thing that's needed for off-CPU flame graphs. Doing custom, you can just do custom stack walking as well. You don't need frame pointers exactly. And I initially wrote the first eBPF stack walker. And doing custom stack walking, we can include other app context. Like if it's a database, what about the database query? You should stick that as a frame in the flame graph, because that may be important. I'd say there's two takeaways. And one is to print out a CPU flame graph of your environment for your office wall. That means you're going to have to use CPU flame graphs. So it's a good takeaway. It's the diagram on the left, the flame graph at Netflix, that's found more performance wins than all my advanced tools on the right. So I do think that is the #1 thing to do because it's just eliminating unnecessary work. There's all these things that you discover when you look at it. Why do I want you to get a CPU flame graph and print it out on your office wall? Later, you will thank me. What happens is 6 months later, there's a regression. And it's like, oh, performance is terrible. You look at a flame graph and you say, is this normal? Do we normally spend time here? Do we normally spend time there? And at Netflix, I would print out microservices and put it on my office wall. And I could just look at it and be like, nope, that's different. So I know you can also do continuous profiling. There's many people do. There's also open source continuous profilers as well. So I'm getting involved in gprofiler, which Intel has acquired. It's an open source continuous profiler. But if you don't have continuous profiling, just printing this out and putting it on your wall gives you a reference to see if anything changed. And then the BPF tools, because that can serve as a type of checklist so that if you know you've got an issue with virtual memory or file systems or something, you can try some things out. There are books on systems performance and BPF. Those are my last 2 books. The slides will be online, and I have lots of references. And I've almost lost my voice from talking to everyone yesterday. It's been really exciting to be back in Perth, and there's so much technology in Perth now. So it's been great. But thank you for letting me introduce eBPF and flame graphs, and I hope they find you lots of awesome performance wins. And thanks for listening to me.
Thank you so much, Brendan. That was amazing. It's really nice to have one of the pioneers in our industry come all the way over to Perth, so I really appreciate that. We're going to open the floor to speakers. We have people online as well, so if you're online, please jump onto the Q&A tab on Hopin and start punching your questions in, and they'll get routed to us. But for now, we'll open it up to the floor. Have we got questions for Brendan?
That was very interesting, thank you. I learned so much. Do you think Apple will add eBPF to the macOS FreeBSD kernel?
You know, that's surprising because Apple work on things privately and they don't tell us. So Apple added dtrace a long time ago. It doesn't fully work now, but the first I heard about it was when they had already put all of my, well, no, they put 40 of my tools in user bin. So, and they didn't tell it because they work in secret. So it's like, surprise, I've now got a bunch of my software is in user bin by default on OS X. So are they working on it? They probably wouldn't tell anyone until it was done. Microsoft at least are working with us. And Microsoft in particular are paving the way for other operating systems. And so I think their work is paving the way for BSD and OS X to follow suit. And there's some great people from Microsoft that are making sure that BPF has been separated when it needs to be from Linux. So we have a separate generic bytecode and we have the separate foundation, and like all of the mechanism, and we have committees to accept changes. And so Microsoft are really pushing the way to make sure that this grows beyond just Linux, and that it is possible for other operating systems. So yeah, Microsoft's work will enable BSD and OS X. It's kind of funny because BSD is where BPF comes from in the first place, and it's going to be Microsoft is basically paving the way for BSD to get back to having the latest BPF. Yes?
Thanks, Brendan. That was a really great talk. Really enjoyed it. You mentioned that BPF has a verifier that gates all the code. I wonder what conditions are verified and how you express those conditions. Like, is there like a DSL for that?
It is, the main documentation is the verifier code itself. We need to come up with better documentations for it. I have done BPF internal talks where I talk about some of the things it looks for. So it looks for backward branches. It looks for unreachable instructions. Programs should have one starting point and one ending point. And there's just endless of these rules that have been added. If you're a BPF developer who's doing BPF bytecode, you are swearing every day at the verifier because it's always rejecting your code. And when I first did this in 2014, there weren't even any helpful error messages. So I'd write stuff and it would just be like, error. It's like, great, I'll try it differently, error. And it's like, I'm just going to mash it and just try it like every different way I can think of and see if I can get it through the verifier. So people are complaining these days about, oh, BPF is so hard. It's like, you think it's hard now when the verifier has like human error messages? Like back in the day, there was nothing. Like I could get a Stack Overflow, there's absolutely nothing at all. So it was super hard in the early days. Fortunately now, there's examples that we do have a Stack Overflow for eBPF. We can ask questions as well. But yeah, if you run into verifier issues, you have to read the source code because it explains all of the rules that it's checking.
Hey, you mentioned manually putting these flame graphs up on the wall and looking at the differences. Are there some automated tools that would do that and detect regressions, things like that?
I would keep all of my, so companies are working on continuous profiling and they're doing flame graphs. We did Flame Commander at Netflix and we did differential flame graphs. So you can compare two different flame graphs. It's harder than it sounds because the Java can inline things differently. So you've got to do the uninline versions of the stack traces so that they're apples to apples. I don't have a go-to company recommendation for this stuff, but I'd say it's an emerging stuff. If you're interested in it, you can probably do cool things and open source them that we will use. At Netflix, I collected lots and lots of profiles. I didn't just have them on my wall, I'd have them in a directory. And when there were issues, I could open the flame graphs up in different tabs, and then I'd blink between them, like looking for planet Pluto, and be like, oh, that tower is moving. This is also one of the reasons why I like keeping it alphabetical or keeping it a consistent axis. Some people change the axis, and it's like, we should sort it based on bigger profile to least bigger profile. And when you do that, things will hop around. The ordering will hop around all the time, so you can't do this visual comparison. And so it's alphabet or call site keeps the ordering consistent from one profile to the next. So that's why I do that. But there are companies that are doing stuff. Intel acquired Granulate. They're taking flame graphs and they analyze the flame graph to see what performance wins can be automatically done by AI. But I'd say it's an emerging space.
Yeah. So you mentioned that BPF can't have unbounded loops. Why is that?
That's a good question. BPF can't have unbounded loops because a BPF program runs with interrupts disabled. So if you got into an infinite loop, your system would be bricked. You'd have to power cycle it. So that's just because of the context that BPF is running. It's a high-level kernel context. So BPF programs have to finish in a certain amount of time. Otherwise, bad things happen. If you disable interrupts for too long, but bad things can queue up and buffer.
Brendan, in the context of, say, a microservice architecture, say 70, 100 services running long-term, or a serverless architecture, what
kind of time range would you be collecting these flame graph data sets for? Would it be by hour, by day, so that you can compare them later? Does that make sense?
Yeah, so it's up to you how do you, it's more of a continuous profiling question. It's up to you how you want to do it. Google has done pioneering work in continuous profiling, and at some point they were doing like 1 hertz profiling on everything 24/7, which sounds very gentle. It sounds like too low to be useful, but over a period of time it is useful because you've got 1 hertz times 60 seconds times 60 minutes. Now you've got enough samples for flame graph. And so when I think about how do we actually deploy this in our environment, it's what is the frequency of continuous profiling? That's one model of doing it, 24/7. At Netflix, we weren't doing that. We were generating a flame graph every hour on, we'd take a microservice, pick an instance, just like a random instance, do a flame graph, save it into S3, and then do that across the Netflix site. And then the Flame Commander UI let you browse the prior flame graphs. You'd say, this is my microservice, and it'd say, okay, here's the prior flame graphs that we collected. What about, I think you asked, like, what about expiry? How long should we keep it for? I don't think Martin and I did any work on that, and so in 5 years from now, Netflix might discover, why do we have so many gigabytes of flame graphs? It's like, oh, there's 2 engineers who just left it running, like forever. So we just left it running. So, but yeah, I mean, I would want to keep them for, I would want to keep representative ones for as long as possible and have some sort of policy for it. The flame graphs themselves, they're not that big. So like you can have a flame graph and it is maybe 5 megabytes or 1 megabyte as a SVG. It's nice to keep the profile as well so that you can regenerate the flame graph or feed it into, sometimes you can feed into the Firefox profile or other tools as well. Questions online?
We have not had any questions come through online. Yep. Just double check. No? So thank you everyone for your questions. Thank you, Brendan. Appreciate your time today. We are going to take a break now for 30 minutes, back at 11 o'clock sharp to hear about reviving the art of software design. So thanks again to Brendan. Cheers.